Change. Okay, so last week we saw the amino acid, the 20 amino acid which compose peptide or proteins. And we said that the amino acids in the peptide protein are linked together by peptide bond between the carboxyl group of one amino acid and the amine group of the other. Okay, in this chapter, we will see how to know the composition and the sequence of this peptide. So the first slide, it's about indeed not the, oh yes, it's the amino acid composition. It means we know how many amino acid of how many amino acid you will have of your peptide and what kind of peptide is it, but you don't know the order of the amino acid in this peptide. Okay, so the first step to know the amino acid composition is to hydrolyze the peptide. So in acid media, you will heat and you have all the amino acid. Okay, with this reaction, heat and in acid media, you will break the peptide bond between all the amino acids. So you will obtain a mixture of amino acid, and after you can analyze this mixture. So we saw that we can analyze this by electrophoresis, but here we can use another techniques, which is chromatography. And after, you remember the dye and we use to analyze the amino acid?
Nitrine?
Yes. So when we add this with nihydrine, we can obtain the absorption of each amino acid. So for example, in this elution profile of peptide hydrolysate, you will have one aspartate, two glycine, one alanine, because the absorption is proportional to the content of amino acid. So here the absorption is double, the absorption of glycine is double than that of alanine. So that two glycine, one alanine, one phenylalanine, and one arginine. Okay, but you don't know which one is the first one and which one is the last one. Okay, it's only the composition. Okay, after that, okay, we can, the next step indeed, it's to identify the N-terminal amino acid. So it means the first amino acid. You remember that for the peptide, we have the first amino acid, it's called the N amino acid, and the C side of the peptide, which with the last amino acid. So when a peptide, so with an amine group, can react with some dye, for example, fluoroamine, we obtain an amine derivative which can be analyzed. Okay, so for example, with the diacetyl fluoride here, this is a dye. It can react with the N side of the peptide, which is this one, Okay, so you label the peptide with the dye, and after you did hydrolysis, and you can analyze only the first peptide, which is usually fluorescence. Okay, so you can identify only the first peptide, because when you make the hydrolysis step, you will break all the peptide bond and you obtain all the other amino acid. Okay, so this is a way to identify the first amino acid. So in this slide, with these techniques, we have the first amino acid and the composition of the peptide. So you have another way to have this time the sequence. So the sequence, it's related to what we call the primary structure. So we will know the composition of amino acid in the peptide, but also we will know the order, okay? Which one is the first amino acid, the second one, and so on. So this technique is called the Edman degradation. And what happened? You have a dye here. The dye will react with the N amino acid, so the first amino acid of the peptide. Here it's alanine. Okay, you will have a reaction, and after, because of this kind of dye, you will release. Indeed, you form a ring, and it will be released from the rest of the peptide. So you have alanine labeled with phenyl isothiocyanate, but you have also the peptide shortened by one residue. This is the first round. Here you have 1, 2, 3, 4, 5, a peptide with 5 amino acids. In the first round, you will label it and release it so you can analyze this, the yellow box. You still have a peptide, so you can label after this and analyze the second box. Okay? So now you can have the sequence of a peptide. Is it okay? You understand the difference between sequence and composition? Okay. So with these techniques, the Edman degradation, usually you have the amino sequence of some only 55 residue in a protein. Okay, so you can make 50 round. So you will know the 51st amino acid of the protein. Okay, so we need another technique to have the whole sequence of protein, because you remember a protein, how many amino acids can have a protein? More than 50. Okay, 50, we said that 50 is the limit between protein and peptide. We will see that after. Okay, so to know the whole sequence of the proteins, we need to divide the protein by several techniques and analyze each peptide that we have. So we have we can cleave the peptide by several techniques. chemical reaction, for example, cyanobromide, or enzymatic reaction, for example, trypsin. Okay. Um, so, for example, I will give you this example. We have a peptide, okay, with trypsin. So we incubate our peptide. You have a question? No? We incubate this peptide with trypsin. So trypsin will break the peptide or cleave the peptide on the C side of lysine or arginine. Okay, so we will have here two peptides. With this technique, we can analyze the two peptides with the Edman degradation, for example. So we will have these two peptides, alanine, tryptophan, and lysine, and tryptophan, phenylalanine, valine, and lysine. But we have these two peptides, but we don't know which one is the N residue. Okay, is it this alanine or is it the threonine? We don't know that. So we make another experiment, for example, with cyanobromide. The cyanobromide will cleave the peptide bond on the C side, here on the C side of methionine. So we will break here. Lysine will break here, the bond, okay? And we obtain, chymotrypsin, sorry. So is another example. We obtain with chymotrypsin. Chymotrypsin will cleave the peptide bond on the C side of aromatic residue like tryptophan. Okay. So with this technique, we obtain only one peptide. It's valine, lysine, alanine, tryptophan. So with this, we can make what we call overlap. So we can overlap the sequence of the peptide, and you can see that the first peptide will be the threonine and the last peptide will be lysine, because with chymotrypsin, you can have valine, lysine, alanine. So here you have valine, lysine, alanine. So the second peptide will be this one. Do you understand that or not, the overlap? We will have an exercise about this. Okay. Let's see after during the exercise. Okay. So in this table, you have the chemical region, for specific cleavage of polypeptide. So you have chemical cleavage. So for example, cyanobromide, the cleavage site is the C site, carboxylic site of methionine, and so on. And usually we use enzymatic cleavage, and you have the name of the enzyme and where they cut the peptide. So, for example, trypsin cleaves the peptide on the C side of lysine and arginine residue. Okay, you don't have to learn this table. I always give you the cleavage site of each region. Okay. So I already answered this question, but what is the difference between peptide and proteins? indeed, we have two definitions. There are two definitions. What is the difference between peptide and proteins?
The can contain other prosthetic group while peptide do not.
Okay, it's not the usual definition.
The class of proteins is over 10,000 kilodalton, otherwise peptides is less than 10 kilodalton.
Okay, it can be a definition. So it's a matter of size. So usually protein has more than 50 amino acid, and peptides so have less than 50 amino acid. It can be a definition. Okay. The other definition, it's more biologic definition. The protein is encoded by DNA. Okay. And the degradation of this protein in the body, in the cell, degradation, give peptide. Okay. So it's another definition. You can have two definitions. The definition between the size, indeed, 50 or less, and the definition between its protein is encoded by DNA. Okay, you remember that what is the average molecular mass of an amino acid, of a residue?
It's 110.
Yes, perfect. Have 110 Dalton. You know what is Dalton? It's almost the same thing that gram by mole. I don't know if you talk with Dalton of gram by mole. Okay. So another definition. So you have here some proteins with molecular weights, the number of residue, and also the number of polypeptide chain. We will see that after. So we will study the myoglobin and the cytochrome C in the last lecture. Okay, you have also, one of you told me that with proteins, so usually proteins has prosthetic groups. So prosthetic group or cofactor, it is quite the same. Cofactor is something that you can add to apoproteins. So apoproteins is the proteins only with amino acid, the polypeptide chain. Cofactor, it's something that it's needed to have the biological activity. So for example, lipids, carbohydrates, so something organic, phosphate group, but you can have also iron, like iron, zinc, calcium, etc. Okay, so if you have the cofactor and the apoprotein, it will call the holoprotein. Protein, holoprotein. Okay, So the cofactor are other compound or other group which give its biological activity to the proteins. Okay, so we have organic or inorganic, as I said, and it can be classified depending on how tightly they bound to an enzyme or to a proteins. So we can have two kinds of cofactor. It's divided in two kinds. You have the coenzyme, which are loosely bound to the protein, and you have prosthetic group who, sorry, it's difficult to write, which are tightly bound to the proteins. Okay. So you have several definitions about cofactor, coenzyme, prosthetic groups. So just remind that this cofactor, coenzyme, prosthetic group are something which is different from the polypeptide chain. It can be lipids, carbohydrates, or iron, but it is needed to have an active enzyme. Okay, the holoprotein will be active and the apoprotein will be inactive. So after we will see several techniques to study, to purify, extracted your enzyme, extracted, purified, and studied the enzyme. So the first one, so the protein must be released from the cell to be purified, and after to be studied to know their function, for example. And in the first step, homogenate is formed by disrupting the cell membrane. So you will disrupting the cell membrane, so it will form the homogenate. And the mixture is fractionated by centrifugation. Okay, so it's called differential centrifugation, sorry. So you will use several rates. In the beginning, you will use a slow rate. You have by centrifugation the supernatant, and here it's called the pellet. And for example, in the first round, you will have in the pellet the nuclear fraction. After that, you have the supernatant, and you do another centrifugation with this time a higher rate and during more time, and you obtain this time in the pellet the mitochondrial fraction. And if you did this again, you will have the microsomal fraction. Okay, so you have to know where is your protein of interest in the cell to do the right centrifugation. Okay, so if you don't know where is your proteins, you will study all the different fractions between supernatant and pellet. Okay.
Can I
Yes.
ask you a question?
Yeah, sure.
So, each step after we centrifugation, do we need to remove the aqueous phase, the upper, the blue phase?
No, indeed.
Oh,
When you did the first centrifugation, you obtain something with the supernatant, aqueous phase, and something which is aggregate. So it's called the pellet. You will take only the supernatant, the aqueous phase, to do the other centrifugation. So you remove the pellet and make another centrifugation with the supernatant. in the second step. And this in the third step, you will remove the pellet and take only the supernatant to make the centrifugation. But sometimes you only have to make only one centrifugation because you know where are your proteins. So you know the rate and the duration of your centrifugation. That's all. Okay? No more questions? Okay, after that we will see that proteins can be purified according to their solubility, their size, charge, and also their binding affinity to other molecules. So in the first graft, it's the first technique. It's called the salting out. Okay, so you know that some proteins at the surface of the proteins, you can have hydrophobic patch and hydrophilic patch. Okay, so it's heterogeneous. You have several surface which can be hydrophobic or hydrophilic. Okay, if you have hydrophilic surface, what happens? The water will go to the hydrophilic phase. When you increase salt concentration, so salt, you will have cation and ion. Okay, around this ion, you will have water molecules. Around the cation and also the ion. Okay, so when you increase the salt concentration, because you have polar groups, this ion will go to the hydrophilic surface of your proteins and help the water molecule to surround the proteins. So you will have in the first beginning of this curve the hydrate shell. It's called the salting in. Okay, so it's, sorry, I forgot to tell you, it's the solubility of your protein against the salt concentration. When you increase the salt concentration, indeed, it should be very high concentration, around 1 molar. Okay, what happened? All the cation and ion need to be surrounded by water molecules. So water molecule prefer to solubilize the ion, so the salt, and there will be no more water molecule around the proteins. So what happened? You will have interaction with these proteins and you will have the precipitation of your protein. Is it clear or not? I try to be clear, but I'm not sure. You have, indeed, you have a competition. You have always water, okay? Because it's the solubility of your proteins in water. The water can surround your proteins, so your protein will be soluble in water, and or your water can surround the ion. Okay, so there is a competition. if the concentration of salt is low, but you have some water molecules surrounding the protein, so you will have something soluble. But if the concentration of salt is too high, all the water will solubilize this salt, and there will be no more water around the proteins. So you will observe the precipitation of your protein. It is called the salting out. Did some of you make organic chemistry or no? It's the same principle. No? Well, I hope you had understood.
Yes. Like the negative charge is salt or protein.
Here it's the salt. The salt is always composed with one positive ion, a cation, and one anion. Okay? The salt. It's only a salt. It means that you have one cation and one ion. And you know that water prefers to be surround ion that hydrophobic surface. Yes?
So we will increase the concentration of the salt step by step, or we decide the final concentration?
You put the salt concentration step by step.
Oh, okay.
And after you will observe the precipitation of your protein.
We will do it continually until get the other
Yes.
precipitation. Okay.
Yes. You increase step by step. Okay?
Okay.
Okay, so when you have your precipitate, okay, you will remove the water and you keep the precipitate. So in your precipitate, you have your proteins. And after that, you put this precipitate in a other buffer. So you will put it in another buffer and you will remove all the salt. To remove all the salt, you use this technique, which is dialysis. Okay, so you know the technique of dialysis. You have a bag, okay, with a membrane, with a cutoff. Oh, sorry. Cutoff number or threshold. So, for example, if we have a dialysis bag with a cutoff of 50 kilodalton, what does it mean? It means that all the molecules smaller than 50 kilodalton can go into the buffer, and all the molecule with a molecular mass higher than 50 kilodalton stay in the bag. Okay, so typically the big one, the red dot, stay in the bag, and the salt, which is the blue dot, can go outside of the bag. Okay, so you will have an equilibrium between what you have in the bag and what you have in the buffer, and you can wash what is on the bag by doing several dialysis. So you will change the buffer So usually 3 times, and you will obtain a protein without or with less buffer. It's a way also to change your buffer. For example, you have, when you did the salting out step, you use, for example, phosphate buffer, for example, because it's the best buffer you had. And after, you have to study your proteins in another buffer, for example, tris buffer. And the way to change the buffer is to use dialysis, and you have the exchange between the two buffer. Okay, is it okay? Do you use it? Do you have practical class or not? Not yet, maybe. Not yet. So after, we will have like techniques, the chromatography. So the chromatography, we have several techniques. I will explain after, but here you have the gel filtration chromatography. So it's also called the side exclusion chromatography. So if you see sec, you will know that it's gel filtration. So gel filtration or size exclusion chromatography, it's the same things. Okay, and here the principle, you will separate your protein according to the size. Okay, in the second yes, in the second, you have the ion exchange chromatography. So sorry, it depends on the charge of the proteins, and here on the affinity to another molecule. Okay, so you have 3 principles: size, charge, or affinity. I will explain that. So the principle of chromatography, so you have 2 phases. No, sorry. You have 2 phases. One mobile phase. So it's usually the gel, and the eluent mobile phase, it's usually the buffer. Okay, and the principle of chromatography, it's like in organic chemistry, it's different. So your protein will go with the eluent or will stay in the mobile phase because of their affinity to the mobile phase or eluent. Oh, sorry, it's not. Sorry, it's not mobile. Stationary phase. Sorry. In the eluent, it's okay. So let's start with the size. The size exclusion chromatography. Okay, in this gel filtration chromatography, you will have beads of diameter of 0.1 millimeter. The beads are made with sugar or polymer, and you have some hole. Okay. And so you can use, when you purchase your gel, you can use the size of the hole, the pore of the pore. Okay. So very small molecule can enter many pore in the gel and stay so in the gel. Okay. The larger molecule cannot enter the pore in the gel, so they will travel rapidly and are elute sooner. Okay, it means that in the side exclusion chromatography, the small molecule will be bound to the gel, and the large molecule will be eluted first. So here, for example, I'll have a mixture of blue and red proteins. The blue one are bigger proteins, the red one are smaller proteins. The smaller protein can go into the beads because there are a lot of pore and they can go inside the pore. And the blue, the bigger proteins cannot go into the beads. So it would be elute first. So in the first time, you have the beads, you have the mixture in the top of your column. And after that, the blue one will travel faster and will be eluted first. Okay. So in the first tube, you will have the blue proteins, and after you will have the smaller proteins, the red one. Okay. So we have this kind of what we call chromatogram. So it will be the amount of solute, usually the absorption, and the volume of effluent or effluent. The volume of effluent, so it's a solvent that you put, it's a mobile phase. Okay. And usually each milliliter, you take a volume of the fraction, each fraction corresponds, for example, for 1 milliliter. Okay. So you will have this kind of chromatogram. Okay. So you have to know. Okay. That what we call the VO, it's the void volume. It's the volume needed for a very, very big proteins to be elute. Okay? It's kind of the volume of your column. And when we plot the logarithm of the molecular weight or molecular mass of your proteins against the ratio between the elution volume and the void volume, you can have a line. The plot is a line because you have something linear between the elution volume and the logarithm of molecular weights. Okay, so when you have an unknown proteins and you want to, it's time that we have the blue. I will answer that after. So you will, if you have an unknown protein, you want to know the size of this protein, what we do? You will make this experiment with standard proteins, that is proteins that you know the molecular weights, and you plot this standard curve, okay, with the blood. And you did the same with your unknown proteins, and you can calculate the volume mass of this. We will have an exercise about that. How do we know when it's time that we have collect all the blue or the red one? Indeed, you have to, it's very difficult, not very difficult, but you have to choose the right solvent. You have to put only few proteins, because what can happen, you can elute in the same time the blue and the red. So to have good separation, you have to try different elution condition. It means the rate of the elution, the concentration of your protein, and so on. So it's not simple than this schema. And you will know, and what we did, we measure the absorption of each fraction. Okay, so you will have the absorption. If you have nothing, you will have no absorption. When you have several your proteins, you will have absorption. So it's indeed, it's not a curve what we plot. It's a dot like this. Because, for example, in 5 fraction, in the 5 fraction, you will have the blue protein. After, you will have something with no protein. And after, you will have the red one. Did I answer to your question? Okay. Okay, after we have the ion exchange chromatography. So here it's ion exchange chromatography. So in the ion exchange chromatography, you have 2 kinds of bits. You have the anion exchange. In this case, the gel or the beads, right, if you need, it's negatively positively charged, sorry. And you have cation exchange. In this case, the gel and the beads will be negatively charged. Okay? So here we have bits which are negatively charged. So here in this example, it's cation exchange chromatography. Okay? When you have anion exchange chromatography, usually the bit it's with amine groups. It's DEAE cellulose. So it's diethylaminoethyl cellulose. Don't remember, just remind this. And when you have a cation exchange, you have carboxylate group, so it's CM cellulose. Okay, so here you have cellulose with amine group. And here you have cellulose with carboxylate group. Okay, so you have the bits which are negatively charged. you will put the mixture of your proteins, and after you will add the buffer here. Yeah. You have to choose correctly your buffer and especially the pH of the buffer, but we will see that. Okay. So when you have positively charged proteins, they will bind to the negatively charged bits. So they prefer to interact with the bits than to go with the buffer. For the negatively charged proteins, they will be so eluate first. Okay, so this is the same. More highly charged protein molecules are more tightly bound to the resin, to the gel, and so they travel slowly and are eluate later. And if you have less charged molecule bits or with the same charge that the bits, they're less strongly bound to the resin and they will be eluate first. Okay, so I saw that when you have a pH diagram, and here the pI of your protein, I remind you that the pI of the proteins, it's a pH for which the protein is neutral. If the pH is lower than the pI, the protein is positively charged. And when it's higher than the pI, the protein is negatively charged. Okay. For example, if we take, two proteins. The first one has a pI at 7. The second one, the B protein, had a pI at 6. And let's say that the pH of the buffer is 8. Okay. So when the pH, the difference between the pH and the pI is high, okay, it means that your protein will be more charged. You will have the protein will be tightly bound. This is the case here with B. Okay, here when the pH, the difference between the pH and the pI is low, so you have a protein which is moderately charged, and so it will moving with the buffer more easily than the protein B. Okay, so for example, here you have a pH at 8. All your protein are positively or negatively charged, A and B. If the buffer pH is 8 and the pI is 6 or 7, what is the charge of your protein?
It will be I think it will be negative.
Yes. So we have negative bits here. Okay. So, sorry, my example is not good. Let's say let's say 9. Sorry. So we have bits which are negatively charged. Okay. We said that protein A is negative, right? And protein B, sorry, I changed the example. It's positively charged. Okay, correct? So it means that because we have negatively charged bits, there's no interaction with A and the bits and the gel, the protein A and the gel. So the protein A will be eluted first. Okay, so you have in the first fraction the protein A. But for protein B, which is positively charged, you have interaction between the bits and B. It means that you have a strong interaction with B and the gel. The B protein cannot be eluted. So we need to elude B. To do that, we have two solutions. We can change the pH. Okay? If we increase the pH at 9, in this case, protein B will be neutral. Okay? So the protein B will not have no more interaction between the bits and B. So it can be eluded. So this is the first solution. The second solution is to increase, the salt concentration. So the red line corresponds to the salt concentration. So chloride, sodium, for it usually. What happens? If we have a lot of iron and cation, what happens? All the cation, so Na+, will interact. All the cation will interact with the bits. So there will be a competition between the sodium ion and protein B. So the protein B will be released because the concentration of sodium ion will increase. Okay? Understood? Okay. No question. Okay. Class chromatography, it's affinity chromatography. So in the bits, you will put a small molecule that you know that this molecule will interact with your protein of interest. For example, you want to purify a glucose binding protein. So you will have bits with glucose graph on or surrounding the bits. You will put your proteins, only the proteins which have affinity with glucose will interact with the bits. And you can remove all the other proteins. And after, to obtain your glucose binding proteins, what we do, you add the glucose. So you will have a competition between the glucose, the free glucose, and the bits grafted with glucose. So all the glucose will bound to the proteins and can be released from the gel. So glucose bending proteins are then released on addition of glucose. The more common affinity colon, it's a colon with antibody. Okay. So you have your antibody grafted onto the gel, and you put all your proteins and only the proteins which interact with the antibody, so the antigen of interest, can be bound to the beads, and all the other proteins will be removed from the colon or released from the gel. So it is the case of non-antibody proteins or antibody of different specificity. And after that, you can have your antigen. Okay. And a simple way to purify the protein of interest is to add what we call a yeast tag. So here you have protein. You know what is a yeast tag? It means that you put at the end, so on the N side or on the C side, a polypeptide with histidine. So usually 6-histidine. It's called yeast tag. You have a beads with nickel and NTA. And what happens when you have your protein with the yeast tag? The yeast tag is complex with nickel, and only the protein with yeast tag can stay in the gel, and all the other proteins will be removed from the gel. So it's a simple way to purify your proteins. Okay. Another technique is the electrophoresis. So the most common electrophoresis is the SDS page. So SDS, polyacrylamide gel electrophoresis. Okay, so SDS, this is this molecule. So this molecule has a negatively charged head and a hydrophobic tail. Okay, so the SDS can interact with the proteins to denaturate the proteins. So you have here the native protein. When you add SDS, you will obtain the denaturate proteins. And because you have a negatively charged SDS, all your proteins will be, negative. So here you have your proteins, we don't know the charge, but at the end you have something negative. Denaturate. So when you put the gel, so the gel is made with acrylamide. It's a composition of the gel. Okay. So you put the gel, you have several walls, and you have the direction of electrophoresis. All your proteins are denaturate with SDS. So all the protein that you put will be negative, and then they will go to the positively charged electrode, and at the beginning you have the negatively charged electrode, and here you have the direction of the electrophoresis. Acrylamide is a polymer, okay? So you have a lot of chain, and at this time, the smaller protein can go faster than the bigger protein, okay? So the slow protein go faster than the bigger one. Okay. Small, big protein. And we can have this relation between the mobility indeed you will measure the distance. For example, you have the gel. You put at the beginning your proteins in the wall, and at the end you will have several depositions. You will measure the distance, this distance between the deposition and the end of the experiment, and this distance of migration, d, you can plot it, and you will have this relation between the logarithm of the molecular weight. You have a plot, a line between this and the distance of migration. Okay? So this is it. So you can do the same experiment at the side exclusion chromatography. If you have an unknown proteins, you want to know its molecular weight, you will make electrophoresis with standard proteins, so proteins that you know the molecular weight. You can plot this curve and obtain your molecular mass. We will have also an exercise about this. Okay. After the SDS stage, usually we make a Western blot experiment. We use antibody. So the first step is the electron transfer. So you have the gel, the SDS gel. You will put a membrane. Usually it's cellulose or something like this. And you make the electrotransfer because your protein are still negatively charged because of the SDS. You put some paper with buffer on the top and the bottom of the gel, and you applied an electric field. So the negatively charged protein will go to the membrane. Okay. So you have all your protein here. You will incubate this sheet with an antibody, wash the excess, and after you can analyze this antibody with adding another antibody, and you have a reaction, a color reaction usually. So this is the Western blot. So you know where are your protein of interest after the separation of your mixture. Okay. After that, we can make 2D electrophoresis, so two-dimensional electrophoresis. So the two-dimensional electrophoresis, in the first time, you have the pH gradient. Okay, so you have low pH and high pH, and you know that the protein will migrate according to the charge. If they are positive, they will go to the high pH, and if the proteins are negative, they will go to the negative, low pH. Okay, they will move until the pH in this gradient is corresponding to their pi, because you know when the pH is equal to the pi, the protein is neutral and they cannot move anymore. So you will have several bands corresponding or are several proteins with the same TI. So the pink protein, maybe you have 4 proteins, but with the same TI. Okay. After that, you will put an SDase gel, and at this time, you will separate the protein according to the size. So in the first step, it will be according to the isoelectric point, and in the second step, it will be separate according to the size. Okay, so here you have an example of what we have. For we don't know what proteins are in this cell. We make isoelectric focusing and SDA page, and we have a lot of plot. Okay. After that, to know which protein, which plot corresponds to which protein, we have to identify each plot. So to do that, we make usually peptide mass fingerprinting. Okay, so we take a plot on the gel. We digest this plot by an enzyme. So we make photolysis of this protein to cut the protein in different peptide fractions. And by mass spectroscopy, we can measure the mass of each peptide. And with the help of a database and a computer, you will have the mass list from unknown protein, and you will compare to theoretical mass list from each entry in the database. And it's the way to identify proteins. So you can have several peptides, and after that, know which is your proteins. Okay. And that's all for today. Maybe you have questions. For the lecture, we have exercise after the break. Maybe with the exercise, you will understand better. No question? Charge of your amino acid. Okay. For example, let's take the example at pH 1. Okay. At pH 1, if we saw that at pH 1, glycine should be positively charged. Every amino acid will be positively charged, right?
Yes.
So it means that if you want to separate your amino acid, you need them to run a distance. So if they are positively charged, it means that they will all migrate to the negative electrode. So you have to depose your here, and all your protein will move to the negative charge. Okay.
Yes. Yes.
And if you have, I don't remember, but if you have amino acid with a double positive charge, it will migrate faster than a protein which had only 1 plus. So you will separate amino acid with different charge. Okay. So for example, in this case, lysine has 2 positive charge, is 2 plus. Glycine, it's only 1 plus. Glutamate, it's only 1 plus. Histidine will be 2 plus. Okay, so at the end, you will have histidine and lysine here, and glu and gly here. Okay? Other question?
And about at pH equals 7, we have like neutral. So we put the mixture at which
In the middle.
in the middle. Okay.
In the middle, because so the neutral amino acid stay in the middle, but lysine will go to the negatively charged electrode and glutamate to the positively charged electrode.
Yeah,
Okay?
okay. Yes.
So for example, we said for exercise 4, sorry. So we have peptide A, which is positively charged, peptide B, which is negatively charged, peptide C, if you did your homework, you should know that it is neutral at pH 6.5. So you will have your paper of your electrophoresis minus. You will depose the mixture of your 3 peptides in the middle. So C will stay in the middle because it's neutral. Peptide B will be here, and peptide A will be here. Okay? So it's very important to know where you put your mixture. Because if you put, for example, if I put my mixture here on the left side, it will be not possible to separate the C and the A, because the C stay here because it's neutral, but the A will be probably move a little only. You understand that? So you will have A and C, which cannot be separated if you put your mixture on the left side of the. Okay? No other question? So let's do the exercise of the day.
Oh, sorry.
Yes?
Because normally when we do the experiment, I don't do the paper, but for the agro gel, we often set up the gel, the well as a middle. So for each case, in this case, so we will put the protein according to the charge at the beginning, instead of put it in the well at the middle of the gel.
Why? And I cannot hear you properly. So why we put the middle? This is the question.
Because we often have the well at the middle, so I think that it will have space for both the negative and positive charge of the protein to separate in two directions.
Yes, because all your proteins, you have proteins will go on different directions. So that's why you put in the middle.
Oh.
If all your proteins are negative, you can put your mixture on the left side. And if all your proteins are negative, they will go to the positively charged and will be separate.
So in here we have the
So in this, we cannot.
Yes.
In this example, because we have several charge, positive, negative, and neutral, you will put in the middle. If we have, so we cannot put on the left or on the right side.
So what happened if we set it at the middle at the beginning and
You don't understand why we put in the middle?
no, I understand why we put in the middle, but I just want to ask because you say that if the protein as a peptide is negative, so we put it in the near the positive charge.
Yes.
Just I want to ask if in case we put the protein at the middle and let it run to the two side of the chart, is okay?
Oh, yes, I understand. But your indeed you need to run your electrophoresis for several times. And the distance of migration of your peptide depends on the time you run your protein, your experiment. So if you have to have the separation, if you put all the protein in the same side, some of them will have no distance to migrate. I don't know if you understand me.
Yes, I understand.
Okay.
Okay. Thank you.
Okay. Other question?
Yes. I have a question.
Yes.
In exercise 4 you wrote 3 negative positively charged, then 2 positively charged, and then 1 positively. So I have a little bit confused that how to we determine that which group release a hydro to when
I heard some music
pH. You cannot hear clearly.
because you have music in background.
Yeah. Yes, in my neighborhood it's very noisy.
Okay.
So
So-
can you hear clearly?
I can hear your question indeed. So
Yes,
you said that you have.
I have a little bit confused when I determine which group release H the hydrogen to when the pH increase.
Oh, the red circle, right? If it's positive or neutral.
Like in the exercise 5, we need to determine that which the shape or which
Yes.
part is in the different pH, right? But yeah, I have a little bit confused that when the positive group release
Okay,
the
I understand.
hydrogen.
Okay. I understand your question. So, for example, let's take arginine. Arginine has a pKa of 11.5, right? So 11.5. Okay. So if the pH is lower than 11.5, arginine will be positively charged. And if the pH is higher than 11.5, it will be neutral. So this is the case of arginine, lysine, histidine, and the N side. It can be positive or neutral. positive or neutral. Okay. Because they are bearing a nitrogen atom, and hydrogen can be positively charged. But if we take, so here it's for arginine. If we take glutamate, for example, glutamate, the side change bear a carboxylic group, so it's oxygen. So at 7.2, this time, when the pH is lower than the pKa, it would be neutral. And when it's higher than the pKa, it will be negative. Okay, so you have here neutral, negative, and also for the C side of your protein. Did I answer your question?
Yes, like so I understand that we not determine all the peptide. So instead of that, we need to determine each amino acid in
Yes.
each peptide.
Yeah.
Yeah, right. Thank you.
So I can give you will see. So for the correction, here you have a higher pH. Okay, at high pH, for example, 13. So you have negatively charged for glutamate and the C side, and neutral for the other. When you have a low pH, at pH 2, for example, all histidine, lysine, the N side, and the arginine are positively charged, and glutamate and the C side are neutral, so it corresponds to that. Okay, and so you have here pH at 5.5. Here for this one you have pH at 11. So when in this case, for example, at pH equal to 5.5, you have some amino acid which are negatively charged and amino acid which are positively charged. You can have ionic interaction between them. So that's why you have this conformation. Okay, and so in this case, you have the last case, you have to determine the pH in which histidine is neutral, so it's higher than 6, and all the other are charged, so lower than 10.5. So here the pH is higher than 6 to have histidine neutral, and it's lower than 10.5 to have lysine positively charged. And in this case, glutamate and the C side are negatively charged. Okay? No other question for this part? So we can make the exercise related to this lesson. So we have in this exercise to determine the position of the disulfide bridge in a peptide. So you remember what is a disulfide bridge? It's when 216 reacted to make a covalent bridge, a covalent bond between them. Okay? This is the disulfide bridge. When you put what is the 2-mercaptoethanol? The 2-mercaptoethanol, it's a molecule, a chemical region, which can the disulfide bridge. Okay, so so when you have a peptide or protein with disulfide bridge, you can break this by putting the 2-mercaptoethanol. Beta or 2-mercaptoethanol is the same. Mercaptoethanol. So you will reduce your protein. Is it okay? Okay. So after purification of a peptide, you can determine the amino acid composition or the sequence of the peptide protein. So a polypeptide was purified after reduction by 2-mercaptoethanol. It means that you put the mercaptoethanol and you reduce all the disulfide bridge. So we obtain the sequence of 2 peptide change, which are this one. Okay? You understand? It means that all the disulfide bridge are removed, are cleaved. So now we have to know where are in the native condition, where are the disulfide bridge. So it's between only cysteine. So to do that, the native polypeptide was treated with thermolysine. So thermolysine, it's an enzyme which hydrolyzes the inside of this residue, leucine, phenylalanine, tryptophan, tyrosine, and valine. It means after bulky hydrophobic residue. After the hydrolysis, the residue composition, so not the sequence, the composition of each peptide is this. So in the first experiment, you have the peptide. We put the reducing agent. Reductant agent. Thermolysine. So you will have the disulfide bridge. And if you put the same, here you have 4 peptides. Here you have 2 peptides. So let's try to do that first. If we did the same experiment, so the third one, with mercaptoethanol and thermolysine, it means that we will obtain the 2 peptides, but with the help of thermolysine, we will cut this peptide after, so on the inside, so before leucine, phenylalanine, tryptophan, tyrosine, and valine. So it means that I will have cut here, tryptophan here, before valine here, tyrosine here, and phenylalanine is here. Okay? So if I did the third experiment in the presence of mercaptoethanol and thermolysine, how many peptides should I have obtained? Hello. Are you? Can you hear me?
Can you repeat the question?
When, if I did experiment 3, I mean, in the presence of mercaptoethanol and in the presence of thermolysine, how many peptides should I take?
4.
4 is without mercaptoethanol.
7.
7, right, because this is what I write in the green line, okay? You remove all the disulfide bridge and after I cut with the green line, okay? So we'll have 1, 2, 3, 4, 5, 6, and 7 peptide. But in the absence of mercaptoethanol, I have only 4 peptides. It means that some of these 7 peptides are linked together by a disulfide bridge. Right? So, for example, the first peptide, asparagine cysteine, okay, it should be linked with another peptide because in the second experiment, I obtain a peptide whose composition are arginine, asparagine, 2 cysteine, and a valine. It means that this cysteine should be linked to this other cysteine. Okay? So you can obtain this amino acid, this peptide, which corresponds to this one. This one corresponds to this one. There's no disulfide bridge. But this one, tryptophan, cysteine, arginine, alanine. So it's tryptophan, cysteine, arginine, alanine. This peptide should be linked by a disulfide bridge to another peptide with tyrosine and another cysteine. So it should be linked with this one. Okay? It means that you have a disulfide bridge between this cysteine and this cysteine. Okay? And the last one. Let's take green one. And the last one corresponds to this peptide with this peptide. To this. Oh, sorry. So it means that you have a disulfide bridge between this cysteine and this cysteine. Is it okay? Do you have question or not?
Can you explain again? It's a bit fast and
Okay. In the first experiment, you only cut this disulfide bridge with the mercaptoethanol, and you obtain the 2 peptides written here. Okay? in the bold colors. In the second experiment, you don't use mercaptoethanol, so you still have the disulfide bridge, but you use thermolysine. So you obtain the 4 peptides which are described here, and you know only the composition, not the sequence. So you know that in the first peptide, you have 2 cysteine, 1 valine, and 1 asparagine. Imagine we did the same experiment, the third experiment, in the presence of mercaptoethanol and in the presence of thermolysine. So, because I would be in the presence of mercaptoethanol, I obtain these 2 peptides, which can be cleaved by the thermolysine. This is my green line. So I should obtain 7 peptides. Okay? Now, because when the disulfide bridge are present, I obtain only 4 peptides. It means that some of the 7 peptides are linked together, right? So let's take the first peptide, asparagine cysteine. It should be linked to another peptide, otherwise you will obtain a peptide of 2 amino acids. It's not the case. You have a peptide with 4 amino acids containing 1 asparagine. So the first peptide in the second experiment is asparagine, 2 cysteine, and 1 valine. It means that the disulfide bridge of the first peptide, it's linked to a cysteine in the peptide containing a valine. This is the case at the end of the second peptide. Understood? And I do the same for the rest of the peptide.
Okay, thank you.
Okay. So let's go to the second exercise. So we would like to determine the primary structure, so the sequence of amino acid of a protein having a disulfide bond, and the amino acid analysis reveals that the polypeptide is composed with 38 residue, and an amino acid is asparagine. So it's N. This protein is then cut into fragments using trypsin. So trypsin will cut, I don't put, on the C side. So cleave the peptide on the C side or lysine or arginine. Okay, something positively charged. And they make the same experiment with cyanobromide. With cyanobromide, it's a chemical reaction. We cleave the peptide on the C side of methionine. Okay, so in this exercise, we did peptide overlap. Okay, so from the first experiment, we obtained 4 peptide fragments, T1, T2, T3, T4, right? But we know that the first amino acid is the N. So if I write my peptide, I will have N, G, A, W, this is my first fragment T1, T2. Okay? But after, I don't know what is the end of this peptide. So I make the second experiment with cyanobromide, and I know that arginine is still the same peptide, is the first peptide, right? So I will put the N and until I will have the same peptide until we will have GRSM. So this is the fragment C1. Okay. So I can continue like this if you understand the exercise. Which fragment should I put after T2?
T1.
Yes, it will be T1. So with the second experiment, it will be
C3.
T3, correct? So and so after so I leave W. So after that, it would be T4. And at the end, T3. Okay? So T3, it's H. Understood the principle of peptide overlap? It's quite easy. No difficulty. So if we answer the question that where are the disulfide bridge, it's between the two cysteines. So you have only two cysteine in this peptide, so it will be here and here. Okay? Tell me if you have question. No question. Next week, you will, I think we will not be able to finish now. So next week, I will start by make the correction, okay, of this exercise. So if you have any question, we can see again this exercise. Okay. So exercise 8, it's about the solubility of proteins. So you have a beta lactoglobulin with an isoelectric point of 5.4. The solubility of this enzyme, of these proteins, in the presence of concentration of chloride sodium solution and at different pH. Okay? So comment and explain this. So you have the PI here. The PI is 5.4. Okay? So why at the PI, the proteins has its lower solubility? So at pH equal to Pi, what is the charge of your protein?
The protein is
Neutral?
Neutral.
Yes, it's neutral. When the pH is lower than the Pi.
It's positive.
Yes. And when it's higher, so it's negative. Okay. So you know that water is a polar molecule. So it prefers the charge, positive or negative, whatever. But when it's neutral in water, you have the lower solubility. Okay. Then the difference between the Pi and the pH value is high. So higher is this difference. Better, sorry, I will, higher is the difference between the Pi and the pH value. Higher is this difference. Better is the solubility. Okay, so that's why when we increase or decrease the pH, we increase the solubility because the difference between pH and Pi is higher. Okay, and if you see the difference between the A, B, and C solution, you increase the salt concentration. Okay, when you increase the salt concentration, so it's quite small concentration, 10 minus 3 to 10 minus 2. Okay, what happened? You make what we call the salting in. If you remind the curve, it's the solubility against the concentration of salt. You have at the beginning what we call the salting in. Okay? Indeed, what happened? You have your proteins. You have some charge. When you have salt, you will have ionic interaction between the salt and your protein with the charge patch. And because you have salt around your protein, you will bring some water at the surface of your protein. So because the cation and anion are surrounded by water molecules, when you have electrostatic interaction, you will bring some water molecule to, near the proteins. So you will increase the solubility. This is the case for low concentration of salt. Okay, so this is the salting in. And after, we will see in the second slide the salting out. This is the case. So here you have if we draw the solubility against the concentration of sulfate, ammonium sulfate, it's also a salt, you will have at the beginning the salting in, and at the end, the salting out. So what happens when the concentration of salt increase? So you have your same proteins with the charge. I don't remember what charge I put. Let's say it's okay. You have the salt here, plus, minus, plus, with your water molecule. You add iron because you increase the concentration of salt. What happens? All the water molecule will help to solubilize the iron. So it means that there's no more the water molecule surrounded the protein. All the water molecule are surround the cation. So you will have the precipitation of your protein. Okay, you have no more water molecule around the protein. Is it okay?
It's okay.
Okay, so using this result, how can we separate the two proteins A and B?
We choose the concentration of the ammonium sulfate at the point that A have already sorting out, but B haven't sorting out.
Yes.
So we can get the A, and after that we increase the sulfate ammonium into the for the B later. Yeah.
Mm-hmm. So, for example, if I put ammonium sulfate at 2.5 molar, A will precipitate and B has his higher concentration, solubility. Okay, it means that you have A as a solid and B as a liquids. So A and B can be separate, right? And after, if you want to extract the B from the other mixture of proteins, you can increase the ammonium sulfite concentration, for example, to 3.5, and you will have the precipitation of B, and you can remove this from the solution. Do you have any question? No question?
No, I don't have questions.
Okay. Thank you to answer. So let's go to exercise 9? Okay. We have two peptides. These peptides are purified using ion exchange chromatography. Indeed, a cation exchange chromatography. It means that the beads are negatively charged. Okay, and we have a buffer at pH 5. You have to tell me, are these peptides bound to the resin? So you have to tell me what is the charge of each peptide. It is positive, negative, or neutral. If it is positively charged, it means that the peptide stay in the resin, is bound to the resin. If it's neutral, this peptide will be eluted. And if it's negatively charged, also it will be eluted first. Okay? So I give you 5 minutes. Maybe half of the class can determine the charge of the first peptide, and the other half can determine the charge of the other peptide. Okay? Can you do that? You need help?
So if we divide into two in the class into two, then who?
Yes, I know. I don't know. You need I tell you the name, or you can do that by your home. Maybe let's say the girl for the first and the boy for the second. I don't know if
No, don't do that. And they only like here. No.
let's do.
Đằng nào
Okay.
chả phải làm.
I don't know. I don't have the list.
I think the boys and the girls are suitable for this situation.
Let's see.
We don't have to divide the class in like perfectly two, right?
No, just do. I mean, you have to practice. So, make one. Each of you should make one. I don't care who did the first and who did the second. Okay? I need the results. And after I can explain to you.
How much time do we have?
I don't know.
Okay.
Because it's in Zoom, I cannot help you. Indeed, because in the class I can help you.
It's okay. We already practiced this, so I just need the time frame.
Okay. 5 or 10 minutes, as you like. or
Okay.
negative.
Yes. Okay. Thank you.
Okay, because I want to explain you the two last exercise, so you have to do that also. So I give you the charge of the peptide according to the pH to the diagram. So if you did properly this diagram, you will see that you have 3 plus here, 2 plus here, plus neutral, negative, 2 negative, and 3 negative. And for peptide 2, it's 5 plus, 4 plus, 3 plus, 2 plus, plus neutral here, and 3 negative. Okay? So it means, so if you have any question about that, I will answer next week, okay? So it means that at pH 5, peptide, so it's here, pH 5, it means that peptide 1 is positively charged and peptide 3 is also positively charged, right? Both protein are bound to the resin because you have ionic interaction between the beads, which are negatively charged, and the protein, which are both positively charged. Okay? Anyway, peptide 2 are more tightly bound to the beads than peptide 1. So normally, peptide 1 should be released, should be evaluate first. So how to proceed to separate these two peptides? Sorry, I will keep because all the proteins are bound together. So we have two ways to evaluate this peptide. For example, I said if we change the pH, it's neutral. So it will be evaluate and peptide 2 still positively charged. So it's still bound to the resin. Okay, this is the first way to separate this peptide. The second way is to increasing the salt concentration. So if you increase the salt concentration, you will have a competition between ionic interaction between the salt and the beads and the proteins and the beads. So in this case, which protein will evaluate first? At pH, we stay at pH 5, for example.
Protein.
Yes, protein peptide 1 or protein 1. Yes, you're right. So protein 1 will be evaluated first. Okay, because this is the one which is less charged. Peptide 2 has 3 positively charged, so it means that it is tightly bound to the resin, and so you need a higher concentration of salt to release peptide 2. Okay. And for the second, the last exercise, I will give you some clue, and you will do that as a homework. Okay. So we have in the exercise 10 a size exclusion chromatography of some proteins. We know the molecular mass of the proteins and the elution volume of your proteins. Okay. So the blue dextran corresponding, it's not VR, but elution volume. Okay. It's a very large proteins, so the void volume will be corresponding to 7.7 milliliter. So you will have to draw, as I told you during my lecture, the logarithm of the molecular weight, molecular mass, sorry, against the ratio between the void, the elution volume and the void volume. So you will obtain a line. Sorry. Okay. The smaller protein will be eluate slower, and the bigger will be eluate first. So for high molecular mass, you will have a smaller elution volume. You will have this kind of curve, so it will call the standard curve. And you can then determine the molecular mass of these unknown proteins. Okay? So you are expected to do that for next week. You can use Excel and what you want, okay? And this is the same in the last exercise. We determine the molecular mass, this time by SDS page, so electrophoresis in the denaturation condition. So you should know that we have negative electrode here, positive here. The direction of the flow is from the negative to the positive electrode. Here you put your mixture of proteins, and so you can measure the distance of migration. The distance of migration is the distance between where you put your mixture and where it arrives at the end. Okay, for example, for albumin, the distance of migration is 1.7 centimeter. Okay, so in this case, you should know that the bigger protein migrates slower and the faster is corresponding to the smaller proteins. And in the same case, you have to plot the logarithm of the molecular mass. Again, the distance of migration. I will make the correction next week. You have to plot 2 curves for next week. It's okay? And if you have any question, about this exercise, about the charge of the peptide, and can make a more complete correction. Other question or not? No question?
No, I don't have question.
No.
I can have my lunch.
Yes. Yeah, we need time to process these, so maybe we will work on the exercise, and then if we have any questions before the next lecture, we will email you.
No problem. I can
or-
answer by email if you need it. No
Yes,
problem.
or
Okay.
we can discuss it in the next lecture.
Yes.
So yeah,
As you want.
I think
By
no one has
email.
any questions.
You have my email, or next week. I will start by a quiz online, as usual, and by the correction of the exercise. Okay? So
Okay.
work, please. See the slide. I will send you the slide and the PDF file of the exercise. Okay?
Okay.
Bye.
Have a nice day. Thank
Bye.
you.
Have a nice evening.